Welcome everybody to my mini lecture series on measurement-based quantum computation. I am Robert Rausendorf and I work at the University of British Columbia, Vancouver. I am the inventor of this scheme of quantum computation, jointly with Hans Briegel, who is at the University of Innsbruck, Austria. This is the first lecture in a mini-series of 4, and it is an overview. If you came to this video by accident and don't know what measurement-based quantum computation is, it is a scheme of universal quantum computation like the circuit model. But unlike the circuit model, which builds on unitary evolution, this computational model is based on measurement. You surely know that measurement is a special type of evolution in quantum mechanics, and for many, it is also a conceptual puzzle. So now that we are all on the same page, let's get started. So maybe this is a good point to start. What you see here in the middle of the slide is a cluster state. And this is a two-dimensional arrangement of qubits. So every blue dot here represents a qubit, and these qubits are entangled in a particular fashion. So measurement-based quantum computation has two ingredients. It has these cluster states and the local measurements. So now let's see what we can make with cluster states and local measurements. And the point is that cluster state entanglement is very flexible and versatile. Here comes the first example. So you see, we are now measuring a bunch of qubits on the cluster. Wherever you see a z, this means that the respective qubit is measured in the eigenbasis of sigma z. And wherever you have an x, this means you measure in the x basis. And those qubits a and b, they remain unmeasured. And the purpose of this measurement pattern is to bring the qubits a and b in a Bell state. So this is something you can do. You can create a Bell state. And you can create that Bell state between any pair of qubits in the cluster. It doesn't have to be here or here. It can really be anywhere. So that's the simplest example of the flexibility of entanglement that is in cluster states. Okay, and now you may want to move away from bipartite entanglement. You want to go to multipartite entanglement. And the simplest example for that would be a Greenberger-Horn-Zeilinger state. So this is now a GHZ state, Greenberger-Horn-Zeilinger state, between parties A, B, and C. And the measurement pattern shown here creates it. And again, well, you will find other measurement patterns that create GHZ states in other places. So again, it's a very flexible construction. You may say, though, that, well, a GHZ state is not so far away from a Bell state. So what else can we do? Here you find a quantum secret sharing scheme. So many parties are involved in this protocol. So the various qubits need to be measured in the bases indicated, and the measurement outcomes have to be propagated and broadcast. And all this amounts to a quantum secret sharing scheme where a unknown quantum state is stored among these 7 parties A through G. Yeah, and quantum secret sharing schemes, they lead us to quantum codes. And there's a particularly useful code that is easily implemented by local measurements on cluster states, and that's the surface code. So again, the yellow qubits are the unmeasured ones, and you can prepare a surface code state on them if you measure the other half of the cluster qubits as indicated. So you see, cluster states and surface codes are very closely related. Now that we've seen these many examples, a question comes up. How far can we take this? The 2D cluster state is a computationally universal material. We can implement any quantum computation on it only by performing measurements. So another analogy is that the 2D cluster state is like a blank sheet of paper, and you're using the measurements to write on it. You basically you imprint a circuit on it by performing these 1-qubit measurements as if you were drawing it. So that's what you can do. You can implement any quantum computation on this blank sheet of paper that the cluster state is. But it doesn't even stop there. When you go to 3-dimensional cluster states, you can obviously still do the same thing. You can be universal, but in addition, you can be fault tolerant. So 3D cluster states are good for universal fault tolerant quantum computation. And again, everything is implemented just by 1-qubit measurements. And that's basically the scope of this lecture: universality and fault tolerance. And then from time to time, we will sprinkle in some background information and some practicalities. So we have finally made it to the outline. So first, here's an outline for the mini-series. So today, I just give an introduction and an overview. And then part 2 is on the universality proof, the proof that measurement-based quantum computation is indeed computationally universal. Then we have one of these practical sprinkles. Namely, we will talk about measurement-based quantum computation with probabilistic quantum gates. So probabilistic heralded, that is. That's important for improving the efficiency of quantum computation with photons. And then part 4 is the fault tolerance that you get with 3-dimensional cluster states. So that was the outline for the mini-series, and now the outline for today's lecture. So we begin with a kind of an overview of measurement-based quantum computation in a nutshell. Then I'll talk about the characteristic features of measurement-based quantum computation. And then I give an overview over experiments that have been performed in the past. And I also tell you a little bit about the history of the subject. Before we discuss measurement-based quantum computation in a nutshell, perhaps it is useful to discuss quantum mechanics in a nutshell. So there is 2 types of evolutions in quantum mechanics that are kind of opposites of one another. So there is unitary evolution, and then there's projective evolution. Unitary evolution is described by the Schrödinger equation. That is, of course, what every student learns first. But then there is projective measurement. And these 2 evolutions, they are very different from one another. So let's begin with the unitary kind. Unitary evolution is deterministic and reversible. So if I have my quantum state fixed at the beginning of time, say at time 0, and I know what my Hamiltonian is, for any later time I will know exactly what state I am dealing with. That state can be a very complicated superposition of basis states, but it is a perfectly well-defined quantum state. And I can know it. Also, this evolution is reversible. So for example, if I have the technological tools to switch my Hamiltonian into minus itself, then I can undo the evolution and get back to where I started. In both respects, measurement is different. So first, measurement is not deterministic, measurement is probabilistic. That is, if I do a measurement on my system, there's no way of knowing what I'm going to get. The outcome is typically really probabilistic, and according to quantum mechanics, cannot be predicted in the individual case. Also, measurement is irreversible. Once the measurement has occurred, it is impossible to go back to the state before measurement. So very different evolutions indeed. But it turns out that universal quantum computation can be based on either. If you use unitary transformations, then you end up with a circuit model, and if you use projective measurements, well, then you end up with measurement-based quantum computation. And so our discussion here in this lecture is about the latter model. So, and after this tiny discussion of quantum mechanics, let's move on to measurement-based quantum computation. So there's actually a lot to say on this slide. So let's say the most important things first. So what you have here in this picture, in the middle of this picture, is a cluster state. It's a highly entangled state of many particles, and we discussed some of those aspects at the beginning of this lecture. And it is a universal resource for quantum computation. So you can use this cluster state to implement any quantum computation you like. And all this is done by local measurements. So information is written onto the cluster, processed and read out by 1 qubit measurements only. So these are the takeaway points. But it is actually helpful to look at this picture for a little longer, because it really contains a lot of information that will be helpful for us in later parts of this lecture. For example, it is also the universality proof in a nutshell. So let's talk a little bit about that. So when we want to prove the universality of this computational model, we'll have to map it to the circuit model. And this figure here shows you how this is done. So you can pick one direction on the cluster, say the horizontal direction, and say, well, this is going to be my simulated network time. And then the perpendicular axis on the cluster becomes your quantum register. So every vertical location specifies the location of a logical qubit. And then these two axes span a canvas, and that's the space in which your circuit simulation lives in. So what we have here, this colored thing, is the simulation of a quantum circuit. So you see horizontal lines, and they are basically the wires in this circuit simulation, and you see bridges connecting these wires, and this will be entangling gates. Okay, so you see a circuit popping out here. Yeah, so let's talk about this a little more. So you begin with a two-dimensional cluster. How do you get this thing that looks like a circuit? What's the first step that you would do? Well, there are these qubits here in between the logical wires, represented by dots. And the dot means that you are measuring these cluster qubits in the eigenbasis of sigma z. The purpose of this is that these qubits will be removed from the cluster. So that is a property that we will later show. And so you see that after these qubits have been measured, you do indeed end up with a network-like structure. All right. So there's more measurements shown here. So every upward pointing arrow represents a qubit being measured in the eigenbasis of sigma x. And what that does is to teleport a logical qubit from one side to the next. The next measurement in sigma z happens, and you teleport further and further and further and further and further. So this is how quantum information is propagated across the cluster. Okay, but so far that is just the identity. That is not very helpful all by itself. But what you can also do is create, and that's again by X measurement, these bridges between two qubit wires. And that mediates interaction among the logical qubit. So that region over here, in fact, is a CNOT gate. So this is how you make logical qubits interact. So what is missing so far? Missing are the 1 qubit rotations about arbitrary axes. And this you can do by changing your measurement basis from the eigenbasis of sigma x towards the eigenbasis of sigma y in varying degree. So this is how you implement logical rotations. And we'll talk about this all in detail. I just want to say the elements are all here. So we have circuits, we have entangling gates, and we have 1-qubit rotations. Okay, so I will come back to this picture when we go over the universality proof in the next lecture. The characteristic features of measurement-based quantum computation. So the first thing we probably have to say when comparing to the circuit model is that measurement-based quantum computation has an appetite for qubits. It uses more qubits than the circuit model would. And the reason for that is simple. In the circuit model, you need as many qubits as your quantum register can fit. But in measurement-based quantum computation, you multiply that number with the number of time steps. That is how many qubits you need, and that can be quite large. First, let's talk about a mitigation for what I just said, namely the fact that measurement-based quantum computation uses more qubits than the circuit model does. So here is a slight variation of measurement-based quantum computation that gets rid of that. So what you can do is here you have a bit of cluster state. On the left-hand side, you burn the cluster using measurements. All right, so that frees qubits up, and then now you bring them in back on the right side and entangle them into a cluster state, and your cluster state just moves on and on and on. So it's a conveyor belt architecture that reuses qubits. It turns out that this type of construction is tremendously useful for quantum computation with photons. But we can maybe talk about it in a slightly more general context. So this construction is useful whenever you have entangling gates that make the cluster, but which are probabilistic yet heralded. So probabilistic is bad. So sometimes these gates function, sometimes they don't. But the good news is they always tell you what happened. And that makes a huge difference. So that when your probability of success is large enough, on average, it turns out that you can grow cluster states. And so you can grow a cluster state on one end, and you take away from it on the other side by performing your local measurements that drive the computation. Now, when you have gates that sometimes succeed and sometimes fail, there is fluctuation. Sometimes the cluster gets larger, sometimes it gets shorter, and you have a safety distance between adding to the cluster on the right and using up the cluster on the left so that the two sides don't interfere. The bottom line of this is it is a very efficient way of doing quantum computation with probabilistic entangling gates, with probabilistic heralded entangling gates. And since it is a matter of practical significance, we actually devote a lecture in this mini-series on that topic. It will be lecture number 3. Okay, but there's more aspects to discuss, so let's move on. So now I'm getting back to the point that I already mentioned earlier, the point about parallelism. So it is good if your physical system where you implement it has inherent parallelism in the interaction. So there is a way of creating cluster states in one step, no matter the size. Such physical systems exist. Namely, whenever you can do the Ising interaction, you can create cluster states in a constant number of steps. So one physical system where this is the case are cold atoms in optical lattices, where you can implement the Ising interaction by cold controlled collisions. Okay, so this is when you have such an interaction, good for measurement-based quantum computation. Another important aspect has to do with protocols that you can do in measurement-based quantum computation. And so one thing that you can do is you can perform secure delegated quantum computation. So that's shown here in this little sketch. So this is you, the client, and let's assume that your quantum capabilities are rather limited. All you can do is prepare 1 qubit quantum states, one at a time, and send them through your quantum internet modem connection to an all-powerful quantum server that then promises you to do a quantum computation for you. But maybe you are a little distrustful. So maybe you want to be able to check that the server is indeed doing what you ask it to do. And furthermore, you want to keep secret what you are computing. And it turns out that this can be done. So this is the paper, if you want to look it up. And it uses measurement-based quantum computation underneath. So measurement-based quantum computation is good for secure delegated quantum computation. Okay, do we have another? Let me check. Yeah, we have one more item, I think. Measurement-based quantum computation is good for distributed quantum computation, fault-tolerant distributed quantum computation. And that has to do with the 3D cluster states that I mentioned in the introduction, which are a fault-tolerant and universal substrate. You can build such a 3D cluster state in a single lab, but you can also stretch it out across the globe. Yeah, and that gives you distributed quantum computation. Let's switch gears now. Let's get a tiny bit technical, although not too technical, just enough to warm up for the next lecture. So this slide is about the creation of cluster states. There is, of course, any number of ways in which you can create cluster states, and this is just one of them. But it is there to illustrate a particular point. So let's get to that. So the procedure has two steps. The first step is that you prepare each qubit in the cluster in an eigenstate of sigma x. Namely, if you want, the positive eigenvalue eigenstate of sigma x. And you can, of course, do this with all those qubits in parallel. So no matter the size, this takes a constant amount of time. Then you switch on the Ising interaction between all pairs of neighboring qubits for a fixed amount of time t. And that amount of time t is given here by this little equation. So it's not a terribly complicated equation. It has an h bar in it. It has the coupling strength of the Ising Hamiltonian in it, and then a bunch of numbers. So this time is given by that relation, and what pops into the eye is that the time you need to switch on the Ising interaction is independent of the number of qubits in the state. It is always the same time. And so the time it takes to create a cluster state in this fashion is independent of the size of the cluster state. So cluster states can be efficiently created if you have the Ising interaction at your disposal. And just as a side remark, and that will become important later, in quantum computation terms, Ising interaction means conditional phase gates. And we'll use that later in the lecture. Okay, so this was one creation procedure for cluster states among many. You could take this as a definition of cluster states if you want to, but we'll see other definitions, equivalent definitions, later on. Let's move on to examples. So obviously the simplest cluster state is the cluster state of 2 qubits, and this is also a state of interest in the quantum information and quantum foundations literature. Namely, up to local unitaries, the 2-qubit cluster state is a Bell state. Okay. Next, simplest example is the 3-qubit cluster state on a line. And that is local unitary equivalent to a Greenberger-Horn-Zeilinger state, a GHZ state. All right, let's spice it up a little bit. Let's look at more elaborate geometries like this wheel shape geometry of 7 qubits in a cluster state, and that's a code word of the 7-qubit Steen code. All right, let me move on to talk a little bit about experiments. Yes, cluster states have been created in the laboratory, and here in optical lattices with cold atoms. This is a physical system that I mentioned earlier, and the mechanism by which the Ising interaction is implemented is cold controlled collisions. So that experiment was just to create the cluster state and measure certain correlations to make sure that it was indeed cluster states that were created. But in optical lattices, measurement-based quantum computation itself has not yet been performed. So this experiment from about 20 years ago is about the creation of cluster states only, creation and verification. So here you have the first experiment that actually experimentally demonstrated measurement-based quantum computation. So that is an experiment that used photonic qubits. And what they did was they created a cluster state of 4 qubits. They demonstrated a universal set of gates, and they even implemented a small algorithm on that system, namely a Grover search on a database with 4 items. We are coming to the end of today's lecture, and I would like to end with a historical remark. Why cluster? Where does this name cluster state come from? What do these states at all have to do with clusters? And that has its reason in experiment. It has its reason in experiment that was performed in David Weiss's group in the late 1990s. So in Munich at the time, Hans Briegel and I were asking ourselves, what can we do with the multi-qubit entangled states that you can create with cold atoms in optical lattices? I mean, these systems were coming online, and it was clear that something interesting would happen in them. So we thought about the question, and eventually we came up with measurement-based quantum computation, but that took some time. At any rate, in all that I said so far, we were assuming these two-dimensional sheet of cluster state. But that was not the experimental situation at the time. So again, we were thinking about using cold atoms in optical lattices as qubits, but it turned out that these optical lattices could not be regularly filled. I mean, there was a considerable degree of control. Namely, it could be arranged such that you have either 0 or 1 atom on each site, but not 2 or more. What you couldn't control was whether that would be 0 atoms or 1 atom. So that was left to probability, and in the experiment they were reaching filling ratios of about 44%, I believe, and their theoretical limit was 50%. So you were dealing with these irregular shapes of qubit occupancy. And now the question was, can you do something with that? And it turned out, for what we were interested in, say, entanglement distribution by measurement, or, well, you name it, the details of shape didn't matter at all. All that matters was that you had connected components and how large these connected components were. So it turned into a percolation problem. If you could fill these lattices at a rate above the percolation threshold, then you would be able to create extended clusters, macroscopic clusters, and that was all that was needed, never mind the shape. And this is how the name cluster state came about. Well, this is really an artifact of history. A little later, in maybe 2002, 2003, the group of Emanuel Bloch and Markus Greiner in München demonstrated the superfluid to mod phase transition, and as a byproduct of this, you could then fill optical lattices in a regular fashion. So the cluster part is now history, but the name nonetheless stuck. Thank you very much for your attention. This brings us to the end of today's lecture, and here you see what's coming up. So the second lecture will be on the universality proof. We will demonstrate that measurement-based quantum computation is indeed universal by mapping it to the circuit model. So today's lecture had almost no technical material at all. That will change. The second lecture will be fairly technical, and it will also be the longest. Then the third lecture will be on a topic that I already introduced today. It will be on measurement-based quantum computation with probabilistic heralded entangling gates and its application to quantum computation with photons. The fourth lecture is going to be on fault-tolerant measurement-based quantum computation on 3D cluster states. I should say I will be somewhat sketchy in that part, so that lecture will be similar in style to today's lecture. There will be a more advanced lecture on the subject. It is a fairly tricky subject, pretty advanced subject, so I think it fits better into a more advanced course on measurement-based quantum computation, which I am also preparing right now. But at least I would like to give you an idea, and that will happen in this fourth lecture. Thank you very much again for your attention.